This lecture talks about the spanning set for a vector space. So if you have a vector space, let's say V, right? And then you're wondering what set of vectors that you can use in order to describe the whole entire subspace. That means you need to come up with a set of vectors. So then all the linear combinations of those sets of vectors will describe the entire vector space. Again, the spanning set of for a vector space related directly to linear combinations of a set of vectors. So if you have given a vector space V, you can try to determine whether a set of vectors is a spanning set for that vector space V. And describing vector space V, that means if you combine all the linear combinations of a set of vectors, you will get to describing the entire subspace V. All right. Well, by the definitions, the set of V1, V2 to Vn is called the spanning set for V, for vector space V. If and only if for all vectors in V, there exists a set of scalars alpha 1 to alpha n such that the vector V here is a linear combinations of V1, V2 to Vn. Again, a set of vectors is a spanning set for a vector space V if and only if you pick a random vector in V, then you'll be able to find a set of scalars a1 alpha 1 to alpha n such that V here is the combinations, linear combinations of V1, V2 to Vn using alpha 1, alpha 2 to alpha n. So using that definitions, we want to put it in practice. Let's say if you want to show that every vector in R3 can be represented as a linear combinations of these three vectors. If you can do that, then that means these three vectors here is a spanning set for V, right? So if you can use these three vectors and to make any vector in R3, then that means these three vectors forms a spanning set for R3. So that's the definition, so that's a theory, but when you put in practice again, you want to use these three vectors and you want to make these three vectors, put it into a matrix. And you augment it with a random vector in R3. So I call it, let's say, B1, B2 to B3. Is a generic vector, right? Because it's the random vector in R3, B1, B2, B3. So if I solve the system, and if I know that the system is consistent, I just need to know that this system here is consistent, then I have at least one solution for this system. So AX equals to B. So if AX equals to B is consistent, then E1, right, E2, E3, these three vectors here forms a spanning set for R3. Okay, so that's how we're going to show whether a set of vectors is a spanning set for R3. Okay. Well, it should be a straightforward task, right? Because now I just need to solve this system. So I have AX equals to B here. And this system is in the correct form already. I have this is a identity matrix. Now I know that x1 equals to b1, x2 equals to b2, x3 equals to b3. Okay. If I found at least one solution, that means my system is consistent, since b1, b2, b3 is a solutions to the system ax equals to b, e1, e2, e3 forms a spanning set for R3. Okay, put it in a system, solve for it, find at least one solutions. That means these three vectors here forms a spanning set for R3. So these are very basic vectors. These are actually E1, E2, E3 are the unit vectors of R3. And so it's easy to solve, right? How about when we look at the next set of vectors? So this set of vectors here is the three vectors, 2, 1, negative 2 transpose, so it's just the column vectors. And you want to figure whether this set of vectors forms a spanning set for R3. Again, we put it in a matrix. 3, 2, negative 2, 2, 2, 0. Augmented with a generic vector, right? Vector V. So again, you want to form, let's say this matrix is the matrix B, X equals to B. Okay, the system that we're looking at. And now the next thing is, if we will be able to determine whether the system is consistent, then this set of vectors forms a vector space. So I want to put out the task. The task is determine whether the system Bx equals to B is consistent. If it's consistent, then the answer is yes. If it's not, the answer is no. Okay, so how can we determine that? We know that we just need to solve for it, right? We need to reduce it. So I reduce this matrix. It's going to give me 2, 3. Well, we want to swipe the second row into the first row. 2, B2, 2, 3, 2, B1, negative 2, negative 2, 0, B3. Okay, my next step is, I just rearrange my rows. Next step is I want to take row 2 and row 2 minus 2 row 1, and row 3 is going to be row 3 plus 2 row 1. Okay, and row 1 stay the same. Want to keep my B's entries consistent. 2 minus 2 is 0, 3 minus 4, negative 1, 2 minus 4 is negative 2, B1 minus 2, B2. And then third row, 2 plus 2 is 0, negative 2 plus 4 is 2, 0 plus 4 is 4, and I have B3 plus 2, B2. Okay, well, I have to do the next step. I keep reducing my matrix, and at this point, I want to take R3 is R3 plus 2 R2, right? 2 plus 2 is 0. That's my next operation there. B2. I keep this the same. B1 minus 2, B2, and this is 0. 2 plus 2 is 0. 4 plus 2 is 4. 4 plus 2 times 2, 4 plus minus 4 is 0. And I have B3 plus 2B2 plus 2 times B1 minus 2B2. Okay. Well, at this point, I ran into a situation where this matrix here, this system here can be inconsistent, because if this side of the arithmetic matrix is not 0, then the system is inconsistent. Right. So at this point, I say if I combine this together, I have B3, 2B2, minus 4 plus 2. So if I combine this together, I have 2B1, right? Minus 4 plus 2 minus 2B2 plus B3. So I can say if 2B1 minus 2B2 plus B3 is different than 0, then the system Bx equals to B is inconsistent. Since the system can be inconsistent for some values of B or for some vectors of B, then that means this set of vectors, here cannot form a spanning set for R3. Keep in mind, a set of vectors forms a spanning set for R3 when the system is consistent for all vectors of B. Since after I reduce this, I try to solve the system here, I run into a problem. And this system can be inconsistent when this value here, right, is not 0. That means it's not true for all value or all vectors of B. So the 3 vectors that we are considering here is not forming a spanning set for R3. So that's how we show a set of vectors spans a vector space, or a set of vectors forms a spanning set for R3. We want to put it into a system, right? With B here is a generic vector. As a random arbitrary vector. And as long as we show that the system is consistent for all vectors B, then the set of vectors forms a spanning set. But if for some value or for some vectors of B for which the system is inconsistent, then the set of vectors here is not forming a spanning set for R3.